So this is Giancoli, Chapter 5, Number 12, Geosynchronous Orbit. Now this is just so cool. I love this. We need a satellite to go around the Earth once every 24 hours. Now, we're going to need it later. Let's figure out what that is. We're going to multiply times 60 minutes in an hour per 1 hour, and then we multiply by 60 seconds per 1 minute. And that gives us 86,400 seconds in a day. We're going to need that. What else do we need? Well, if you look at the satellite, what do we have? We've got the gravitational attraction, and that's it. So I don't know, we call that the plus y direction. And what we have to have is an acceleration downward. We got to have that radial acceleration. Well, let's just do Newton's second law for this one. Newton's second law in the y direction. We get the sum of the forces in the y direction is equal to the gravitational force. So that's big G, big M, little m over r squared. But that has to equal to my radial acceleration, which is just mv squared over r. And this is a neat thing. The weight of the satellite doesn't matter. So we can actually do calculations for the satellite. Now, we have to do one more thing. We have to say, well, what's v? V is equal to 2 pi r, distance around, time, over the time. And then, therefore, v squared is going to be 4 pi squared r squared over t squared. We're going to put that into this equation here. So we're going to get g m over r squared equals v squared, which is 4 pi squared r squared over t squared. And don't forget, we've got one more r. That's going to cancel one there. And now we can see, moving like all the constants to one side, we find g m over 4 pi squared. That's just a constant, depends on the central body, is equal to r cubed over t squared. And this is the famous r cubed t squared rule that Kepler found before he even knew any of this. So we can actually do calculations. Now, what's the altitude? So what's the height above? So we're looking for r, where this satellite is above the, well, we're going to do Earth surfaces. Well, we're going to do from the radius from the center. Then we're going to have to subtract the radius of the Earth, and that'll give me my r0. So what we know is r cubed, let's solve this one, is gm over 4 pi squared times t squared. Now we know what that is in seconds. And so now we can actually do our calculation for the we're going to take the cube root of both sides, but let's just do do it. 6.67 times 10 to the minus 11. Mass of the Earth is 5.98 times 10 to the 24. All of these you can find. Divide by 4, and then I got to get my pi. Where's my pi? Is right. Give me a second. I can find. Oh, there it is. Pi, and then I got to square it, which will be, every calculator is different. Divided by, and multiply by 86,400. And then I take the cube root. 1/3, raise it. That's not right. Let's try that again. 6.67 times 10 to the minus 11. A mass of the Earth, 5.98 times 10 to the 24 times 4 divided by, I can find my pi again. We got to square it, divided by, and we take 86,400 and square that, times, and then we take the cube root. Let's see if it works this time. And I get, that's better. So this time I get 42, let's call it 44.2 times 10 to the 7 meters. Now, the radius of the Earth, what's the radius of the Earth is, what do I have here? 4.22. Radius of the Earth is, I think it's 3.6 times 10 to the minus 6 meters. We're going to have to check that. So I subtract that, 3.6 times 10 to the 6. And I find that my radius for my motion, that's what I did. That's my radius of the Earth. So RO is equal to R minus RE. That's going to be equal to 3.8. We're going to have to call it 3.9. 3.9 times 10 to the 7 meters. So that's where If you want a satellite to go around once every 24 hours, that's what the height you have to put it. That's the only height. And you will find a lot of satellites at that height. And in part B, we're going to look at satellite speed, and we'll also look at how it compares to a 200 kilometer satellite above the Earth.